Oh, hello there. Well, I got my vitamin C and it looks like I'm ready for a pre-calc lesson for the day. Today, we're just going to kind of finish up what I like to call playing around with some polar graphs. So, have your calculator handy as we get into some examples on page 10 of the polar packet. A joke for you first. Did you hear about the bed bugs who fell in love? Yeah, it was great. They got married in the spring. I would say go to the middle of page 10 now and then pause the video so you can try these conversions on your own because you're going to find them to be very quick. 9, 10, and 11. Then rejoin and let's check answers with one another. We need to convert to rectangular form. All right, let's start with 9 and 10. Man, well, these look like they're just, this is sitting here on a silver platter for us, right? I know r cosine of theta is always equal to x when I'm converting. So an x equals 2, and how about our sine of theta, a y equals 4 for the second one. In terms of a shape, they're both going to be lines. You've got a vertical line represented by x equals 2 and a horizontal line represented by y equals 4. Okay, so no big surprise there. 11 doesn't look too bad either. We've converted tougher equations than these. What are we going to do to get this in terms of x's and y's? Well, the conversion equations I know of are mostly in terms of the trig functions sine, cosine, and or tangent. So let's rewrite this in terms of sine, cosine, and or tangent, right? Instead of writing secant, we know we can always put a 1 over cosine of theta. Now let's multiply over, right? Get rid of the fraction. R equals 4 cosine of theta. And we want to do something smart that can get us an easy substitution in terms of x and or y to get this rectangular. And I say double good would be to multiply both sides by r, which is a technique that we've used before. It's double good, like I said, because you get an r squared on the left side. There's an easy sub in for that. And then watch this r join the other side, making that easy substitution as an x like we used in the last problem. So I know on the right, I'll just have 4x, and on the left, I get x squared plus y squared. I don't know if I knew it right away just by looking at it. Maybe by the time I got here, I might have recognized it from yesterday's lesson in the summary of features of graphs, but this is definitely going to be a circle. And right now, one move would get it into general form. I guess just moving the 4x over. So x squared plus y squared plus 4x equals 0. Some more, I should say minus 4x, right? Subtracting the 4x to the other side. And a couple more moves could get me the center and radius if somebody needed to see this in standard form of a conic section. For fun, yesterday we enjoyed graphing a bunch of these on the calculator. Let me try to graph this original on the calculator, and I should probably go from the version that's solved for r. R equals 4 cosine of theta. So just for fun, let me grab my calculator here. I'll make sure nobody's been messing with my mode. You don't want to mess with my mode. I'll go to polar mode instead of function. I've got my window set up to graph in radians, which is going to be good for this trig setup. Theta max 2 pi. Theta step, how about pi over 24? And you'll see plenty of this if you graph it from -5 to 5 on both the y-axis and the x-axis. So let me go to y equals, clear out any equations that might be in r equals, and I'll type in 4, just cosine of theta. So a simple graph, the likes of which we've seen before. I will hit graph, and you get a circle. Now, what did we do to remedy the fact that this looks more like an egg on its side? It looks more like an oval. I can hit zoom square as a quick fix. Zoom 5 will make it look more like a proper circle. And also, I want you to think of symmetry. Because this equation is an r equals in terms of cosine, its major axis of symmetry here, or really which way you're traveling out to get to that center of 2, 0, is going to be the polar axis, versus a sine curve that would give you an off-center circle that would be oriented upward from where the origin is. Okay, not too much craziness with those problems. I really like number 12, though. 12 is my favorite on the page. It says, man, we have solved, let's walk down memory lane. We have solved many a system of equations and inequalities in our day. We've solved systems of linear, quadratic, higher degree polynomials. We solved systems of conic sections just in this exact unit. And now I think I just might cry. I'll try to hold back the tears as we solve our first system of polar equations. So it doesn't look too bad. R equals, we have to figure out where these two graphs meet. R equals 1 sine of theta and R equals 2 a 1 plus sine of theta and r equals 2 sine of theta. Let me get that right. I want to see if you could predict what these graphs are going to look like. Eventually, we'll go to a calculator, but not quite yet. Do you remember this shape? It's a 1 plus 1 sine of theta. That's a cardioid. That's your heart shape because A and B, these coefficients are the same exact number. So this one's going to be some sort of heart shape, and it'll either go up like this or down like this because the axis of symmetry needs to be vertical if it's in terms of sine. And then this, just like the conversation we just had, should be an off-center circle that should sprout up from the origin. Same reasoning with that sine being the axis of symmetry. And we want to find any and all points of intersection of these two polar graphs. Well, all our algebraic techniques should hold up here. So I want to go with substitution for starters. I want to, if this is r and that is r, I want to equate the two expressions. 1 plus sine of theta, I want to know where that will equal 2 sine of theta, and I hope I can trust our algebra skills here. Let's consolidate. I'm going to move everything to the right-hand side and get 0 equals, let's subtract sine from both sides, and get sine of theta minus 1. Okay, not too bad. Now get sine by itself. I need to figure out any and all places where the sine of theta equals 1. Where the sine of theta equals 1, we should have an r comma theta, a solution to both polar equations. Well, where is the sine equal to 1? How many times would that happen if you're just traveling once around the unit circle? I know sine is the y-coordinate on the unit circle, and it only happens up at pi over 2. You have these coordinates, 0, 1, where the y, the sine, is 1. So I'm going to say theta equals pi over 2. And that's the only solution I've come up with right now. Now we'll check the graph in a second to make sure that this still looks good. And I'm not quite finished, right? If I'm finding the solution to a system of equations, I don't just stop at one part of the solution. I want my answer to be an ordered pair. I want the theta along with the r value that matches with that theta. Well, no problem. Take this answer, this theta equals pi over 2, and you decide which one you want to sub it back into of the two originals. I'll pick the top one. R equals 1 plus sine of pi over 2. We'll solve this. Well, we just talked about the sine of pi over 2 being 1. R equals 2. You've come out 2 circles to get to that point. So I want to commit to one solution, one intersection point between these two polar graphs, and it's going to be at this ordered pair, 2 comma pi over 2. Now, if I trust my algebra, I should be on my merry way and get on to some other bigger and better question. But there's a little more than meets the eye to this question. Why don't we look at a graph of these two polar equations? So I'm going to go back to my calculator, clear out the equation that I had in there previously, the 4 cosine of theta, and replace it with a 1 plus sine of theta. We said this should be a cardioid. And my r sub 2 is just going to be 2 sine of theta, an off-centered circle. Again, we are in polar mode, we're in radian mode, and our window is 0 to 2 pi for the thetas, a theta step of, we'll say, pi over 24. Window for x's and y's doesn't matter too much now. This is the picture that you get. I'll zoom in a little bit. I'll go to window and notice that I really don't need negative 8 to 8. So let me go negative, how about 3 to 3 for the x's, and we'll do the same thing for the y's, negative 3 to 3. And if we want this to look more symmetric, in a second, we can follow it up with a zoom square. See how it looks a little bit squashed? So I'll follow that up with zoom 5. And now I see something that I could have predicted, right? But does anything throw you off? Is anybody not comfortable with the fact that we didn't get a second solution? Check out this graph. Do you see your answer on this graph? Do you see theta of pi over 2 and an r of 2? Well, yeah. Pi over 2, you come up to 90 degrees, and you're coming out 2 circles. We've just found the first intersection point up here. Is it the only intersection point? By algebra, it's the only intersection point. I didn't find any other answers to those equations we were solving, and I trusted our methods. But what about the origin? It looks like those two graphs meet at the origin. If I zoom in, both of them hit 0, 0. So here's the big debate. Is 0, 0 a second answer to this system of equations? And the answer is no, and I'm going to prove to you why. Sure, both functions hit 0, 0, but it's not a common point for both graphs because it doesn't happen at the same time. What I mean by that is, sure, the point 0, 0 is attained, but not at the same theta value. Think about it. If you're coming out 0 radii on the circle, you could have any theta you want if your r is 0, and your point is always going to be on the origin. So I want to prove to you that this middle point is not an intersection by looking at the table. Now that you have both equations in your y equals, can you go to the table by hitting second? And actually, I want to go to my table settings first. So second in window for table set. These are the settings of your table. And I'll start my table at 0. But what I want to do is, for simplicity of typing these numbers in, can you hit mode with me real quick? Let's go to mode. Let's go down to degree mode. I want to type these values in degrees instead of radians. What will the function still be graphed if I hit graph? Well, sure, if I expand something. I'll go to window, and instead of going 0 to 2 pi, can you make it 0 to 360 degrees? We'll try that. Theta step, instead of pi over 24, I'll say 7.5 degrees. Everything else I'm going to keep the same. And I'll hit graph to make sure I still see the picture, but in degree mode instead of radians. Now that I'm in degree mode, let's go back to our table settings. Start at 0 degrees, and I want you to just graph the quadrantals. I want my theta, or my delta table, what the table is going to count by, to be 90 degrees. So I'll put a 90 in here and set both of these on auto, so the independent and dependent variable values get filled in automatically. Let's check out the table. It should show us what's happening on both graphs simultaneously. Do you see our intersection points on this table? I hope you do. So where do I see an intersection point? It looks like at 90 degrees, and every angle coterminal with 90 degrees, 450, 810 is another one. Both graphs are hitting the R value 2 at the exact same time for the exact same theta value. Sure, both graphs hit 0 at random times, but do you ever see 0 in the same exact line, right, for the same theta value on both graphs? And it's just not happening. So both graphs hit 0 at certain points, but not for the same theta value. So moral of the story, we trust our gut, right? There is one solution to this system of equations, and that is 2 pi over 2. I will catch you in the next one.